Hi there, how's it going? We're going to go through another stress analysis problem in this Mechanics of Solids, Mechanics of Materials video. The problem involves a shaft that's got some loads creating bending. So we're going to look at the stress that, the maximum stress that's developed, and then turn it into a kind of a simple design problem by inverting the analysis problem. So let's have a look at it and see how we go. Right, so here's the problem. So we've got this shaft supported at end A here by a thrust bearing. So the thrust bearing means that it can't move horizontally, and being a bearing, it can't move vertically as well. And then we've just got a journal bearing at D, so it's restrained in the vertical direction but free to move in the horizontal direction. Then we've got these two pulleys that presumably have belts going to some other part of the machinery that's not shown, that are generating these 3 kilonewton loads here. And we're told that the shaft is a hollow circular shaft with an outer radius of 40 mil, inner radius of 25 mil. And we're asked to determine the absolute maximum bending stress that occurs in this shaft. All right, so let's start working through the solution. So first step is, well, let's just write down the equation that we need to use. So if we're looking at the shaft in bending, then we can use our beam flexure formula. The maximum stress is the maximum bending moment that occurs in the beam, or in this case the shaft, times the distance from the centroid to the outer fibre, divided by the cross-sectional moment of inertia. Right, so first thing we need to do, though, is to determine the reactions at the supports so that we can then determine our internal moment. So previously we've looked at determining shear force and bending moment diagrams. So we'll determine the bending moment diagram for this shaft so that we can find the maximum moment. And then we'll need to work out the moment of inertia, or the second moment of area, for this cross-sectional shape that we have. All right, so firstly, the free body diagram of the shaft. Just draw the shaft, apply the loads, and then think about what's happening at the supports. So at the left-hand end here, we have a thrust bearing. So we could put on horizontal force as well, but I can see that there's no other horizontal forces acting, so I've just left it off on this free body diagram. We have a vertical reaction A, so if we take moments about point D, for example, these two 3 kilonewton forces tending to cause an anti-clockwise rotation about D, so therefore we need RA to be acting upwards, causing a clockwise rotation, and then RD over here from some of the forces in the vertical direction must be equal to 0, so RD will be acting upwards. Or we can, from symmetry, know that these two forces, RA and RD, must be equal to each other and also equal to 3 kilonewtons. Okay, but really you should have the full justification from some of the moments and some of the forces. All right, so we've got our reaction forces there, RA and RD equal to 3 kilonewtons. Now if we determine our internal bending moment, so if we take a section, or we look at the section AB and take a cut somewhere through section AB and draw a free body diagram of one side or the other. So we'll take a cut through here and look at the left-hand side, put on our external force RA, which is our reaction, define where the cut is with our variable X, put on the internal actions, internal shear force and internal bending moment. We don't need the shear force in this problem. If we were looking to calculate shear stresses, then we would, but we're just going to look at the bending moment for this problem. So taking moments about the cut end, we can calculate our internal bending moment as MAB equals 3 times X, or So we could have RA times X, but I've just put 3 in here straight away. All right, so that's our equation for the bending moment in section AB at X equals 0. So at end A here, the bending moment equals 0. And then at 0.75, when we get to where the pulley is, our bending moment is 3 times 0.75, so that's 2.25 kilonewton meters. Then if we look at section BC, take a cut somewhere through section BC, put on our external load, so we have our reaction at A. We now have the force from the pulley at B acting downwards. Put on some dimensions, indicate where the cut is using our variable X. Put on our internal actions, shear force and bending moment. Right, so we've used the positive sign convention for shear force and bending moment here. Right, take moments about the cut end. All right, so I've done this one first. So this 3 here. The distance from the cut is X minus 0.75 times 3, tending to cause an anti-clockwise moment. All right, so this is a little bit tricky because I've taken a shortcut. All right, and I can see that this moment is in the same direction as MBC, so therefore when I put it on the other side of the equal sign, it becomes minus. Right? So if you need to do the intermediate step where you just work from left to right or right to left or whatever, and put them all equal to 0 and then rearrange the equation, then do that. All right, so then we've also got RA times X here as a moment about the cut. That's going in the opposite sense to MBC, so therefore when I put it on the other side of the equal sign, it will have the same sign as MBC here. All right, so rearranging this equation, so RA, remember, was equal to 3. So here we have minus 3x plus 3x, so that becomes 0. So we just have minus 3 times 0.75 gives us 2.25 kilonewton meters. All right, so what that shows us is that the bending moment is constant between B and C here. Right? So if we have pure bending between B and C, and the other thing you can see here, of course, is if you do some of the forces in the vertical direction, you'll have RA minus 3. RA is 3, so 3 minus 3 is 0, so therefore the shear force must be equal to 0 between B and C. All right, so here we have pure bending between the 2 pulleys. All right, so if we now draw our bending moment diagram, we can see that we start from 0, linearly increasing to 2.25 at the pulley B. Then we have a constant 2.25 between the 2 pulleys, and then at C we'll come back down linearly to 0 at point D, which is 0.75 plus 1.5 plus 0.75 is 3 meters. So that's what I've got down here. All right, so we've now worked out that our maximum bending moment in the shaft is 2.25 kilonewton meters. So now if we make use of our beam flexure equation, so we need the distance from the centroid to the outer fiber, so that's just the radius. So now calculating our moment of inertia. So we have a circular cross section here, so we can look up the back of the book in the appendices and find the moments of inertia of the common shapes. So circle is a common shape, and we can see that its moment of inertia about a centroid will be pi r to the 4th on 4. So here we've got a composite shape, a circle inside another one, so we can add up the moments of inertia, just the outside circle minus the moment of inertia of the inside circle. So that's how we get to here. Put those values in, and we get a moment of inertia of 1.704 by 10 to the minus 6 meters to the 4th. Right, so we're going to now put all our values that we've just calculated into our beam flexure equation. 2.25 by 10 to the 3, because I've converted kilonewtons into newtons here. 0.04 is the is C that we looked at here, and then our moment of inertia. From our calculator, we get 52.82 by 10 to the 6 newtons per meter squared, or 52.82 by 10 to the 6 pascals. Got a bit of a storm going on outside. I'm not sure if you can hear that thunder or not. And then we can convert that to megapascals. So 10 to the 6 is mega. So that is 52.8 megapascals. All right, so that's the end of that part of the problem. For the UTS students doing this as a tutorial problem, what I also asked you to do was to, if the allowable normal stress for the material in this shaft was 150 megapascals, what's the minimum required outer diameter for the shaft? I said to just assume that we're going to keep this same ratio between the outer and inner radii or diameters for the shaft. So this is 1.6 here. So yeah, just finishing that part of the problem. The maximum stress was 52.8. So to determine the minimum required outer diameter, if the allowable normal stress was 150 megapascals. Now note that this is not the yield stress. Because this is a shaft, you know, normally I don't really like doing this simple approach to design for a shaft that's rotating, right? Because really you should, if it's a rotating shaft in bending, then you really should be doing a fatigue analysis, okay? But just as a demonstration and just to do something simple to start with, we've turned this analysis problem into a simple design problem. Okay, so assuming that the allowable stress that we're given here takes into account the fatigue. Also, we haven't taken into account any stress concentration effects. All right, so this is a very simplified approach, and if you're going to design this shaft properly and actually put it into commission in practice, then you need to do more than this simple approach that we're doing here. But anyway, for now, let's have a look at how we might go about doing this simple design problem. So, as I said, we're going to keep the same ratio between the outer and inner radii or diameters. So our maximum stress from the beam flexure equation, maximum bending moment, distance from the centroid to the outer fibre divided by the moment of inertia. As we had before, we just use that same equation for the moment of inertia for the hollow cylinder. So pi over 4 r naught to the fourth minus the inner radius to the fourth. So the inner radius is just RO divided by 1.6. So just rearrange this equation here. So hopefully you can see where that's come from. Taking RO outside of the brackets here. Okay, so here we'll get RO to the power 4. So we can take that outside the brackets and we're left with 1 minus 1 over 1.6 to the power 4. Because what we're going to need to do in this design approach is to take R naught over to the left-hand side of the equation and make that the subject of our equation. All right, so the allowable stress is, so we've got here, so substitute here for our maximum stress now the allowable stress, and what we've got here. So we've got the maximum, our bending moment, the distance from the centroid to the outer fibre is R naught, and then we've got this expression here underneath for pi. Right? So I've just substituted this into here. All right, so doing a little bit more rearranging of equations. So we've got RO on the top here, RO to the fourth on the bottom, so that becomes RO to the power 3, and the pi on 4 here, the 4 just comes up to the top. Right, so now if we rearrange this equation, so we want to make R naught the subject of the equation, so we need to bring that around here. Right, so R naught to the power 3 over to the left here, right, becomes on the right hand side the cube root of what we had on the right hand side over here. Right. Hopefully that makes sense. So now that we have that, we can substitute our values that we had before. Right. Something a little bit different that I've done here. So now I've got 2.25 by 10 to the 6, whereas previously I had 2.25 by 10 to the 3. So what I've done here is to work in newtons, millimeters, and megapascals. Right, so here I've converted 2.25 kilonewton meters into 2.25 newton millimeters. Right, so the kilonewtons becomes 10 to the 3 newtons, the meters becomes 10 to the 3 millimeters. So that's why it's 10 to the 6. And then we've got 150 in megapascals. So that gives me an answer in millimeters straight away. Right, so I get 28.25 millimeters. So that gives me a outer diameter required of 57 millimeters. This is not too bad in terms of trying to rearrange the equation to make R naught the subject of the equation, but it can get messier than this. All right. So what you can do, I think you probably heard that bit of thunder. So what you can do instead is to use Excel. So I'm going to show you how I've modeled this problem in Excel. Okay, so here I have my Excel spreadsheet, and I've just set it up. So I've, rather than just putting in this equation and putting M in directly, I've put in some of the other parameters that make up the problem. So, if I really was doing a design problem, I might need to change these values. Right, so here I've got the length LAB. So let's go back to problem here. Right, so length LAB is 0.75, length BC is 1.5, length CD is 0.75, and so on, right? So the other thing that you might notice is when I click on these things, right, so in my equations here, instead of having cell references, right, I've got these names. So here I've got the loads and the reactions. So when I calculate M max here, so here it was the reaction times length LAB in my calculations on my working out over here. So the reaction force 3 here times 0.75. So in Excel, what I've done is, so that my equations are a little bit more meaningful, I've defined some names. Right? So the way you do that, all right, so let's say here, like here I've got 1.6 for the ratio. So let's, instead of doing that, let's go in here, go plus, and go call this ratio, and I call this 1.6. Right, so if I wanted to change this, so normally what you would do is click on this and go here, right? See how it's now a cell reference, B7. I'm not sure if that's, you can see that or not. All right, but anyway, this is R to the naught over B7, right? So that's what normally happens. If I undo that and I go down here, where's my ratio? So here now, if I right click in that cell, I can define the name. Right, so I go define name, and it already looks to the left and says, oh, there's something to the left here. Do you want to call this thing ratio? Right, so I just say yes, call that ratio. And then when I go down here and I change my formula and I click in that cell, right, it now sees that as being a cell called ratio rather than being a cell called B7. So let's do that now. All right, so that's setting up the model and defining names. What I've got here at the moment is the answer. So let's change this back to what I want to start with. So 0.04. And all right, so the inner radius updates. And we can see that we get the same value for the stress that I calculated before. So if I go to the next page here, right, so I get 52.8 for my stress. And then the next part of the problem was to say, right, let's turn this into a design problem and say, if we've got an allowable stress of 150 megapascals, what diameter do I need? Right, so you could do it by trial and error. So you could guess, all right, so we got a stress of 52, and we want a stress of 150, so let's make it 0.08 and see what we get. All right, so obviously it went the wrong way. I wasn't thinking about my design problem properly. So here I've got a stress of 6.6 megapascals, so that's way too low, right? So obviously went the wrong way there. So I need 0.0, let's try 3. Right, so I've got 125 megapascals now. So, you can keep doing that, but that's not very clever, right? There must be a better way of doing that, and of course there is. And the clever way to do it is to use what-if analysis and use goal-seek. Right, so unfortunately this is pretty small. Hopefully you can see that. So in goal-seek, I need to set my cell to a certain value by changing some other value. So I want to change this cell here to be 150 megapascals, and I want to do that by changing my outer diameter or the outer radius. Right? So if I do that now and let it do its thing, it now tells me that I need an outer radius of 0.0282 millimeters, so a bit smaller than the 0.04 that we had before. And now here I've just multiplied that by 2000 to get it into millimeters as a outer diameter. So normally when we're specifying the size of a shaft like this, we'd specify diameter rather than a radius. So that's why I asked for diameter rather than radius here. So that's how you change the problem. All right, so what if we said, oh, okay, we need to change some things. We can't actually have it to be 0.75. We need it to be a bit shorter than that. So let's make it 0.7. And I've assumed here in my modeling that the design intent is for this thing to be symmetrical. So when I set up the model, I set the length on the right-hand side here to be the same as the left-hand side. So my loads are still the same, and now my bending moment is less. Okay. So now the stress is 140. So I can do that again. So let's redo my what-if analysis. Let's do goal-seek and set cell naught. Oh, no, we want this cell, don't we? We want to change this one. We want to change this cell to be that cell for the stress. We want that to be 150. And we want to do that by changing. I'm going to try this and see what happens. Yeah, okay. All right, you've got to have the value that you're using before this calculation. All right, so we've done that. So now we get a required diameter of 56 millimeters. All right, so that's the end of the problem. Hopefully that was interesting and helpful. Extended the simple textbook problem a little bit beyond just what's written in the textbook, and turned a simple analysis problem into a simple design problem. All right, that's it for now. See you in the next video. Bye.